Imagine walking through Yellowstone, steam drifting from hot springs, geysers hissing, and the ground beneath your feet alive in a way that feels almost unnatural. Now picture hearing that the park is splitting apart. Would you imagine the land tearing open like a movie scene, with fire and ash erupting into the sky? That's exactly the picture sensational headlines want you to believe. But is it true? Could one of the most visited national parks on Earth really be on the verge of ripping itself open and unleashing a disaster beyond comprehension? Or is something far more fascinating and far less apocalyptic unfolding beneath the surface? Yellowstone has always carried an aura of mystery. Tourists stand mesmerized by Old Faithful, unaware that just beneath them lies a magmatic system vast enough to have shaped entire landscapes. It is little wonder, then, that stories of impending doom capture the public imagination. After all, the idea of a supervolcano erupting in our lifetime is terrifying. But here's the real question. Does Yellowstone actually give us any reason to fear that kind of catastrophe right now? Or are we misreading the slow and subtle signals of a living Earth? Scientists are quick to point out that Yellowstone cannot be understood in isolation. To understand what the ground is doing here, you have to first zoom out, not just to Wyoming, but to all of North America. The continent itself is on the move, drifting slowly westward, while rotating ever so slightly counterclockwise. It sounds dramatic, but the pace is barely a few centimeters per year. Still, those centimeters matter, because they form the baseline against which Yellowstone's own movements can be detected. Without accounting for this continental drift, the park's subtle deformations would look like random noise. It's a bit like standing on a moving train while trying to figure out if the book on the table in front of you has shifted. Until you account for the train's motion, you can't really judge what the book is doing. Once scientists subtract this continental drift, Yellowstone's patterns become visible. GPS stations placed across the region reveal that parts of the land northeast of the caldera are inching eastward, while those to the southwest are creeping southwestward. The ground is not cracking apart in dramatic fashion, but it is stretching, almost as though the park is caught between two subtle but opposing tugs. Does that mean the Earth is splitting in two beneath Yellowstone? Not exactly. What we are really witnessing is part of a much larger process, the slow extension of the crust that defines much of the western United States. This stretching, called basin and range extension, has been reshaping the region for more than 15 million years. From the rugged valleys of Nevada to the Sierra Nevada mountains in California, the crust has been thinning and pulling apart.
Yellowstone just happens to sit on the northeastern edge of this vast geologic province, which explains why its crust appears to be splitting. It's not the park alone tearing itself open, but a continuation of a continental story that has been written for millions of years. Consider this. In 1959, the Hebgen Lake earthquake struck just outside Yellowstone. With a magnitude of 7.3, it was powerful enough to trigger landslides and alter the landscape. But this quake wasn't a prelude to volcanic doom. It was the result of normal faulting, the kind that happens when the crust is stretched and parts of it drop down. This was a blunt reminder that the forces shaping Yellowstone are not confined to magma lurking underground, but also involve tectonic stretching on a continental scale. The reality is complex. Yellowstone's fault system is a patchwork that reflects multiple overlapping processes. Some faults formed when massive eruptions in the past caused the ground to collapse, leaving behind circular fractures known as ring faults. Others trace their origins to the inflation and deflation of the caldera floor as magma and hydrothermal fluids shifted below. Layered over all of this are the regional tectonic stresses that have been pulling Western North America apart for millions of years. When headlines scream that Yellowstone is splitting, they are simplifying a symphony of processes into a single, terrifying storyline. The truth is more intricate and, in many ways, more fascinating. So, where does Yellowstone's volcanic energy actually come from? The park sits above what geologists call a hotspot, a deep plume of mantle material that has been fueling volcanic activity for at least 16 million years. This hotspot has left a scar across the Snake River Plain in Idaho, marking the trail of past eruptions as the North American plate drifted over it. Every so often, the plume generated enormous eruptions, 3 of which formed the Yellowstone caldera itself. Those eruptions were on a scale almost unimaginable today. Around 2.1 million years ago, 1.3 million years ago, and 640,000 years ago, Yellowstone unleashed super eruptions that blasted ash across huge swaths of North America. The last of these spread a blanket of ash covering about 7,500 square kilometers, with particles drifting as far as Iowa and even into the Pacific Ocean. To put that in perspective, the 1991 eruption of Mount Pinatubo in the Philippines, one of the largest in the 20th century, was tiny compared to Yellowstone's prehistoric blasts. Yet, here is the paradox. Since that colossal eruption 640,000 years ago, Yellowstone has been relatively quiet in comparison. Instead of catastrophic blasts, it has produced lava flows, hydrothermal explosions, and, of course, the iconic geysers that draw millions of visitors each year. Statistically, the interval between its last 3 super eruptions averages about 725.
But that number is deeply misleading. Volcanoes don't operate on human calendars. 3 data points do not form a reliable schedule, and scientists caution strongly against assuming Yellowstone is overdue. In fact, the park may remain quiet for tens of thousands or even hundreds of thousands of years. So why the uncertainty? Because Yellowstone's magmatic system is not a simple cauldron of liquid magma sitting under pressure, ready to blow. Thanks to modern seismic imaging, scientists now know the structure beneath Yellowstone in remarkable detail. Beneath the park lie 2 massive magma reservoirs. An upper chamber about 5 to 15 kilometers deep, and a lower one stretching from 20 to 45 kilometers. Together, they contain thousands of cubic kilometers of partially molten rock. That sounds frightening. But here's the catch. Only a small fraction of it is actually liquid. The upper chamber, for instance, is estimated to be about 9% molten. The deeper reservoir contains even less, only a few percent melt. Imagine looking at a block of ice with small pockets of water trapped inside. It's not the same as having a bucket full of liquid water. Out of roughly 4,000 cubic kilometers of rock beneath Yellowstone, only about 1/4 of a Grand Canyon's worth is truly liquid magma. The rest is solidified rock infused with scattered pockets of melt. This means Yellowstone is not sitting on a ready-to-erupt vat of magma. Instead, it's more like a hot, mushy sponge deep underground. Even more intriguing is the possibility that Yellowstone regulates itself. Recent studies suggest that a shallow magma layer about 4 kilometers beneath the surface acts as a kind of pressure valve. It traps heat and gas, but instead of letting them build up catastrophically, it releases them slowly through the hydrothermal system. The very geysers, hot springs, and fumaroles tourists marvel at. Earthquakes and small eruptions may also act as minor release valves. In this way, Yellowstone breathes, preventing the kind of sudden overpressure that might trigger a massive eruption. With this in mind, what are the actual odds of a super eruption in our lifetime? Statistically, they are vanishingly small. Based on geological records, scientists estimate the annual probability at around 0.00014%, roughly 1 in 700,000 per year. By contrast, smaller volcanic events, hydrothermal explosions, and earthquakes are far more likely and far more immediate concerns. The most damaging hydrothermal blasts in Yellowstone's past have carved craters hundreds of meters wide. Locally destructive, yes, but nowhere near the apocalyptic scenarios so often portrayed. And yet, the question persists. Could Yellowstone erupt again on a super scale? Over geologic time, yes. But the conditions required are specific and rare. Large volumes of rhyolitic magma must accumulate, remain molten, and become gas-rich enough to fragment explosively. At present, the system beneath Yellowstone does not meet those conditions. The reservoirs are too crystalline, too mushy, and too stable to unleash a sudden catastrophe. If Yellowstone is not a ticking time bomb, then how do scientists actually know what's happening beneath the surface? The answer lies in a remarkable array of monitoring systems that track the park's every shiver, sigh, and breath. The first layer of this watchful eye is the GPS network. Receivers across Yellowstone measure ground movements on the scale of millimeters per year. Subtle shifts that most visitors would never notice, but which reveal volumes about the park's inner workings. Over the years, GPS data has shown that the caldera floor rises and falls by a few centimeters, sometimes inflating for several years before settling back down. To the untrained eye, that might look alarming, but to geophysicists, it's a natural expression of fluids, magma, water, or gases moving through the crust. The caldera is alive, but not in crisis. Take, for example, the inflation episode in the early 2000s. Over the span of just a few years, parts of the caldera swelled by several centimeters. Headlines declared the supervolcano was reawakening, but scientists remained calm. Why? Because these pulses of inflation have happened before and are usually followed by subsidence, the ground slowly sinking back to its prior level. It's Yellowstone's version of breathing in and out. If you or I took a deep breath, no one would assume we were about to scream. Yellowstone, too, inhales and exhales. Then there are the earthquakes. Yellowstone is one of the most seismically active regions in the United States, recording thousands of quakes each year. The vast majority, however, are tiny, less than magnitude 2, and go unnoticed by visitors. Many occur in swarms, clusters of small quakes happening over days or weeks. These swarms often spark public concern, yet they usually reflect hydrothermal fluids moving through cracks, rather than magma surging toward the surface. It's as though the park's underground plumbing gurgles and sputters from time to time. Scientists carefully distinguish between tectonic quakes, which come from stresses in the Earth's crust, and volcanic quakes, which are linked to magma movement. The last truly major tectonic event near Yellowstone was the 1959 Hebgen Lake quake at magnitude 7.3, outside the caldera itself. Since then, the largest quakes inside Yellowstone have been moderate at best. None have carried the telltale signs of imminent eruption. The ground shakes, yes, but not with the rhythm of rising magma. To peer deeper, scientists use seismic tomography, essentially creating a CAT scan of the Earth using earthquake waves. These images reveal the structure of Yellowstone's magma reservoirs. The shallow chamber sits about 3 to 9 miles deep, while a larger, deeper reservoir extends to roughly 12 to 28 miles. The shallow one contains more evolved rhyolitic magma, while the deeper one houses hotter basaltic magma. For a supereruption to occur, vast amounts of rhyolite must accumulate and remain molten. But right now, the conditions fall far short of that requirement. This is where the picture gets more intriguing. Hydrothermal activity, the geysers, hot springs, fumaroles, and mud pots that captivate millions of visitors, acts as a pressure valve for the system. Rather than trapping all its heat and gases underground, Yellowstone releases them in spectacular displays. The same forces that create geysers like Old Faithful are also preventing the kind of dangerous buildup that might lead to catastrophe. In essence, Yellowstone vents its frustrations in the open, letting off steam both literally and figuratively. Yet, hydrothermal activity carries its own risks. While not civilization-ending, hydrothermal explosions can be violent and destructive on a local scale. Imagine a pocket of superheated water trapped beneath the surface suddenly flashing to steam. The result can be an explosion powerful enough to hurl rock, water, and debris across hundreds of meters. Craters hundreds of meters wide testify to such events in Yellowstone's past. About 13,000 years ago, one such explosion in Mary Bay carved a massive crater in Yellowstone Lake. Though devastating locally, such blasts are nothing like a supereruption. They are reminders that the park's greatest hazards are often the smaller, sudden events, rather than the apocalyptic ones. So why is Yellowstone stretching apart at all? The answer lies not only in the hotspot below, but also in the tectonic forces surrounding it. Yellowstone sits at the edge of the Basin and Range Province, a vast region where the crust of Western North America has been thinning and pulling apart for 15 million years. Normal faults create mountain ranges and valleys, shaping the rugged landscapes of Nevada, Utah, and beyond. Yellowstone is caught at the northeastern fringe of this zone of extension. Its splitting is not unique, nor is it a prophecy of volcanic disaster. It is part of the continent's ongoing geological evolution, slow and steady, on the timescale of human lives, but dramatic across millions of years. If that seems like a lot to keep track of, consider the arsenal of technology scientists now employ to monitor Yellowstone. GPS, seismic arrays, satellite radar interferometry, INSAR, and gas sensors provide real-time data. In recent years, INSAR has detected seasonal inflations and deflations linked not to magma, but to snowmelt and groundwater. Even groundwater levels can subtly change the measurements, curd, but the top
Precise the science has become. The more data collected, the clearer the picture. Yellowstone is dynamic, but its current movements are normal for an active volcanic system. Expert voices consistently push back against alarmist narratives. Michael Poland, the scientist in charge at the Yellowstone Volcano Observatory, has emphasized again and again that there are no signs of an impending supereruption. Peer-reviewed studies in leading journals echo this. Supereruptions are not just rare, they require conditions Yellowstone does not presently have. Even the biggest volcanic disasters of recorded history, the eruption of Tambora in 1815, which caused the infamous Year Without a Summer, or the 1991 eruption of Mount Pinatubo, were small compared to Yellowstone's ancient eruptions, and even those had clear warning signs for months beforehand. This is perhaps the most important point for the public to understand. A Yellowstone supereruption, if it were to happen, would not occur without warning. Significant uplift, intense earthquake swarms, unusual gas emissions, and dramatic changes in hydrothermal features would all signal that something extraordinary was brewing. Right now, none of those signs exist. Yellowstone is restless, but not threatening. And this leads to a bigger question. Why do we gravitate so strongly toward doomsday narratives about Yellowstone? Perhaps it's the human fascination with catastrophe, the allure of imagining forces so vast they dwarf our own existence. Or perhaps it's simply that fear spreads faster than nuance. Yellowstone splitting apart makes a gripping headline. Yellowstone is slowly stretching due to regional tectonics, while venting heat through hydrothermal systems does not. Yet it is the second version that carries the truth. Maybe the real story is even more interesting than the disaster movie. Yellowstone is one of Earth's great natural laboratories, offering scientists a chance to study how mantle plumes, tectonic forces, and hydrothermal systems interact in real time. Few places on the planet provide such a vivid window into the inner workings of Earth. The geysers and hot springs are not just tourist attractions, they are expressions of a planetary machine humming just beneath our feet. So instead of asking, when will Yellowstone erupt and destroy us? Perhaps the better question is, what can Yellowstone teach us about how our planet works? The more we learn, the better prepared humanity becomes, not only for Yellowstone's eventual future, but also for volcanic hazards across the globe.
And here's the part worth reflecting on. Even if, tens of thousands or hundreds of thousands of years from now, Yellowstone does produce another supereruption, who's to say what humanity will look like then? Our technology, our monitoring systems, even our ability to mitigate such events may be unrecognizable compared to today. And if you want more explorations into the mysteries of Earth, make sure to like, share, and subscribe. Because the real story of Yellowstone, and of our world, is just beginning to unfold.